Okay. So my name is Metin. I'm a PhD here in Oslo, and I'm going to talk about ZodiPy. So since we are about to integrate high-frequency data sets such as Derby, HFI to the Cosmoglobe framework, we need to build a Zodiacal emission module for Commander. And ZodiPy is a first milestone towards this goal. And so ZodiPy is this Python tool which we have built that's capable of predicting the zodiacal emission as seen by an arbitrary solar system observer. Before I talk more about this tool, I'm sure that not everyone's familiar with zodiacal emission, since it's not typically a foreground in CMB context. It dominates in the infrared frequencies, but it's becoming more and more important nowadays as we increase our precision. So this is a phenomenon known as the zodiacal light. Maybe some of you have seen this with your own eyes before, but essentially it's light that shows up just before or after sunset in this cone-like structure following the ecliptic. And it's the result of sunlight scattering of interplanetary dust particles, or grains rather, and these are distributed around in the solar system, mainly along the ecliptic, and they can be categorized or subcategorized rather into these components. So we have the zodiacal cloud, which essentially encapsulates the entire solar system, and then there's these asteroid belts or bands, but I'll come back to this later. And so in addition to scattering sunlight, these grains are also heated by the sunlight, and as a consequence, they emit thermal radiation, mostly in the infrared, but also at high microwave frequencies. And this becomes a source of contamination for our data. So here are two sets of two data sets. So here we have the IRIS data, and here we have the Derby data. And I should just quickly mention that these maps are in galactic coordinates, while the zodiacal emission, or the interplanetary dust, is aligned along the ecliptic, which kind of makes this S shape in these maps. So that's why they look kind of weird if you haven't seen this before. Yeah, and this is relevant for both current but also future experiments. So JWST, from their background tool, you can see that SOLDI dominates a pretty big chunk of their spectra. And this is from Ken Ganga's recent paper on interplanetary dust emission in LightBird. And they also expect to detect some zodiacal emission, similar to what Planck did. So zodiacal emission is a bit different compared to most regular foregrounds that we're used to think about. And this is due to how close it is to us or the observer. And this can be illustrated like in this example. So if you imagine that an observer that's inside the dust distribution, and the observer is now looking at a point on the distant celestial sphere at two different times during its orbit around the sun, we can clearly see that these line of sights contain different amount of interplanetary dust. And so what does this mean, and what does it look like in practice? Well, like Daniel talked about, we have gotten our hands on the Derby data, and this is a GIF that I've made where I've essentially binned the Derby CIOs into weak maps. And here we can clearly see that this zodiacal emission, that's this bright blob, it is moving along the ecliptic. And it's hard to imagine that one so-called foreground template could describe this nicely. And like Daniel said, this data is very small. So this GIF I was able to make in under a minute in Python. So it's a very nice data set to work with. But even if you imagine that you would like take the average of all of these weeks, you would get something like this. And even here, the signal is not very, it's not clear that you can make a single template for this, because there's still a remnants of the scanning strategy and other cuts, etc. here. And that's why typically to deal with Zodiacal emission, you need to correct for it in the data processing part, in the time-ordered part of the data processing. And the question is then, how do you do that? And the first step is to figure out how the dust is distributed in the solar system. So for this, you need an interplanetary dust model. And this is typically a 3D parametric model, which splits the dust distribution into several components. The most familiar one of these is the Derby model or the Kelsall model, and this includes 6 such components. So we have the diffuse cloud, which is the major contributor to the overall dust density, and it essentially encapsulates the solar system. And these images are essentially, they are cross sections, one perpendicular to the ecliptic and one along the ecliptic, which show the dust density distribution. You also have the certain solar ring, which is dust particles falling in towards the sun, which has gotten trapped in Earth's orbit, with an extra enhancement in the region trailing the Earth. And then finally, you have 3 dust bands, and these are associated with different asteroid families, and they appear a bit further away in the solar system. So once you have such a model, it's not that bad to evaluate the emission. Essentially, what you end up doing is you make an assumption for what the emission mechanisms is, and that's typically some sort of modified blackbody. And so then you end up having to solve a bunch of line of sight integrals from the observer through the dust distribution. And this is the integral that you have to solve then. So you have the number density of a zodiacal component. You have the Planck function and the dust temperature, which is a function of distance from the sun. And then you have an emissivity, which corrects for the deviation from an actual blackbody. And then you just evaluate this integral over the line of sight, which is then evaluated at the heliocentric coordinates given by this. So you have the observer's position in the distribution and then the line of sight. And this is perfectly fine to use at CMB frequencies, because there you don't expect any scattering of sunlight. But if you want to evaluate the model at infrared frequencies, or far infrared rather, then you can include a scattering term. And this is the equation from the Derby paper, where they construct this model. And here they've added a scattering term, which consists of an albedo, which essentially says something about what's the probability that this dust component will scatter some sunlight at this wavelength. And then there's the solar irradiance, which is how strong is the, how intense is the sun at this, at some wavelength, at a distance from the sun. And then there's a phase function and a scattering angle, which is what's the probability that the scattered light enters your line of sight. And yeah, so once you have the model and you're ready to solve these line of sights, that's essentially all you need to do. And what we have done is that we have created ZodiPy, which essentially solves these line of sights for arbitrary solar system observers. And here's a minimal usage of the code. So you'll initialize the model given, for instance, either the Derby model or the Planck 18. And the Planck 18 here is just an extension of the Derby model to CMB frequencies. So if you want it to be valid at CMB frequencies, then you pick Planck 18. And then all you do is you specify an observer, a time of observation, a wavelength, and some angles, or optionally a pixel number. And this can also be a sequence. And then you'll get the predicted emission. And typically you would want to use this in a chunk-wise manner. So you have a chunk of time-ordered data for which you can assume a constant observer position. You should make sure that you have fine chunks, so no greater than 1 day, because remember the zodiacal emission moves roughly 1 degree per day on the sky. So this is a time stream created with ZodiPy, and if you remember from Daniel's talk, you probably recognize this structure. And we have also compared this with the output of the Derby zodiacal light prediction software, for which we find an agreement, a very good agreement. So the error or the difference is less than 0.2%. And here is a preliminary usage of ZodiPy on the Derby data, where we have taken a weekly Derby data map, and we have used ZodiPy over the same pointing period. And then this is the residual. And again, this is for the full Derby data. And so there's a lot of other stuff you can do with ZodiPy. I'm not going to go into all of that, but you can make so-called instantaneous maps, which is essentially what does the zodiacal emission look like at a particular day. And so here are 2 maps in ecliptic coordinates with the sun as an orange dot. This is 6 months apart, and here in galactic coordinates. You can also get the component-wise emission, and this can be useful if you observe some weird residual and you want to see if it's one or the other component. That is, if one of the components, if the signal clearly looks like, for instance, this thing, then you know it's the feature responsible. So putting this into the context of Cosmoglobe and Commander, what we have done so far is that we've developed the standalone ZodiPy code. And what we want to do next is that we want to integrate this into Commander. And once we make sure that this is able to correctly reproduce the zodiacal corrections that ZodiPy does, then what we want to do is we want to build a Gibbs sampler which can sample all the IPD model, interplanetary dust model parameters, because the Kelsall model is from the 90s, and the parameters are very degenerate with each other. There's over 83 parameters, and hopefully once we include the HFI and Derby datasets into the powerful framework that is Commander, we can perhaps derive a better interplanetary dust model. So let's see if there's something I forgot. Yes, so ZodiPy also allows for extrapolation of the built-in models to other frequencies. So you can, if your experiment is observing at another frequency where none of these models are valid, you can do an extrapolation, see what that looks like. And you can also provide it with custom interplanetary dust models, either by specifying completely new components or by changing the parameters in the existing components. And we're also working on a paper to accompany ZodiPy, so be on the lookout for that. And if you want to learn more about this, please check out ZodiPy either on the GitHub or on the cosmoglobe.io page, where I think you can find it on the front page if you scroll down. And I think that's all I had to say. Thank you for the funding.